Hello, everyone, and thank you for joining us today. We have a very interesting webinar ahead, and we'll get started in about 30 seconds, just wanting to give people time to join in. Hello, everyone, and thank you for joining us today. We know you're very busy. You have many things to accomplish before the end of the business day, and we really appreciate you taking or choosing to spend this time with us. We have a very interesting webinar planned, and we hope you find it interesting and informative. This is going to be part 4 of a series of 5 webinars. And the topic is using graph algorithms for advanced analytics. And this is part 4, and we're looking at similarity algorithms. Next slide. My name's David Ronald, Director of Product Marketing, and I'm delighted to introduce the presenter, Victor Lee. Victor has a very interesting background. He's very accomplished in a number of fields. He has a BS in electrical engineering and computer science from UC Berkeley, and an MS in electrical engineering from Stanford University, 2 of the top universities in not only America, but in the world. And he has a PhD in computer science from Kent State University. He focused on graph data mining as part of that PhD thesis. He's also taught graph in the past, and he has over 20 years experience in the tech industry. Before we get started, there are 3 housekeeping items to run through quickly. These webinars are intended to be as informative as possible, and indeed we like them to be as interactive as possible, and we encourage you to submit your questions. You can do that at any time by clicking on the Q&A button, typing in your question, and we will do our very best to answer everybody's questions today. Next, this webinar is being recorded and it will be uploaded to our website shortly. We typically get that done in about 2 to 3 hours, and around the same time we will send out an email which will include a link to that webinar along with the slides and maybe any scripts or any other relevant material that we think will be useful. We'll include in that email, and additionally you can go to that URL of your own accord and view the archive there. And last but not least, if you have any issues with Zoom, please contact us and we'll do our best to troubleshoot them as quickly as possible. So without further ado, I'd like to pass things over to my colleague, Victor.
Thank you, David. And thank you everyone for joining us. Again, this is the 4th in our series on graph algorithms. So it's been pretty exciting to keep building on this topic because it has been a progression. So I'm going to do a little bit of recap of parts 1 to 3, and then get into talking about similarity. So detecting whether 2 things are equal is easy, at least in concept. I know it can be computationally hard, but defining what does it mean for 2 things to be exactly equal is fairly straightforward. Defining what it means to be similar is a little bit trickier because you have to think, well, what things do I care about? And then we'll start, excuse me, go into some of the common approaches for similarity, which have been written. There are a couple common algorithms which originally were not written for graph, but we offer some graph-oriented versions. And those are both local similarity algorithms. And then we'll talk about global similarity and what that means. And then, of course, we'll do some demo using GSQL, Graph Studio, and those algorithms. So to review, in this series, we've been presenting algorithms as common known tools that you can use to help analyze your graphs. So you want to become familiar with the tools so that you become an expert builder, so to speak. And as a builder, you may eventually see how you want to combine multiple algorithms to perform a larger and more complex task. And we motivated this by looking at some common questions, some more pragmatic questions that people may want to know for their use case. So for example, in your data set, which entity is most centrally located? Is that a physical location or more of an abstract conceptual location in terms of communication or transporting information? And we addressed that in Graph Gurus 27. And at the same one, we also looked at the question of how much influence does one entity exert over another, which interestingly can also be measured or thought of as centrality. Who is the most influential? So it's a sort of a ranking thing, and PageRank answers that. In Graph Gurus, by the way, 26 was on shortest path algorithms. 29 was on community detection, and that's when you want to group things. You have a graph of data, but within that graph, there might be natural subgroups based on their level of connection, which ones are more connected to others. And today we're going to look at similarity. And sometimes people get community detection and similarity a little bit confused, or at least they see them overlap, because there can be overlap. But the key here is we're not going to be looking at connections as necessarily what makes them similar. We're going to be looking at other properties. So again, this is a quick summary of the previous 3 parts of the graph algorithm series. Shortest paths, really, we spent a lot of time introducing the whole topic of graph algorithms and the GSQL Graph Studio platform that we would use. And because shortest path algorithms are actually pretty straightforward, the only thing to remember is that are your edges directed or undirected? And are they weighted or unweighted? Because there are actually different algorithms you want to use for those different cases. You can use a general purpose one, but that general purpose one will be overkill, will take longer if you have unweighted edges, for example. Centrality, again, so we're abstracting, it could be physical location, or it could be a more abstract concept of location and travel. And there were 2 different ways of looking at this, closeness and betweenness. And betweenness is actually the one that's maybe a little bit different. Think of the entity as being on the path to get from one place to another. Like thinking about, you want your gas station to be at a crossroads. It itself is not a destination that excites people, but it's something that people will always find along their way. That's betweenness. And we talked about why PageRank is also a form of centrality, and we described PageRank, how it's calculated and what the exact interpretation is, because you've probably all heard of it, particularly in the context of web pages. But if you want to use it for something other than web pages, you have to really understand, well, what is it telling me? If I choose to use it, how is it going to rank things? So, because that's how you decide, is this really the right algorithm to use or not? And last time, I believe this was just 2 weeks ago, we talked about community detection and how this is really about looking typically at relative connectivity. You're in the group if you're more highly connected with the other members of the group. And then, though there are several very black and white rule systems, such as just connected component detection. Just because you have a graph, just because it's one data set, and that data set is a graph, does not mean that every entity has some connection to some other thing. There may be some isolated parts, which are called components. So each part that has no connection to any other part is called a component. And one of the most important algorithms is to sometimes find those components, because that's a precursor to running other algorithms. Other algorithms will assume that, for example, PageRank will assume that you're dealing with just one connected component. So an important preliminary step is to find those connected components. We also talked about how it could be a post step. Say you want to find the most influential members in a medical care community, for example. And then once you find out who those influential members are, then you can find the community around them. It just makes me think about these days when we're all thinking very rationally about, how do we try to minimize the impact of coronavirus, and, finding hubs and understanding propagation is a really important question there. So today, similarity. So let's get into it. So start by looking again at a use case in health practices. And, healthcare, it's obviously very important because it deals with our fundamental wellness, our health. And it also can be a very expensive venture. So we want to make sure we're giving people the best healthcare possible, and we want to make sure that we're doing it in the best way possible, so that we can, do it with the most efficiently, so that we can actually use our finite resources to help the most people. So, here's a dashboard where we're looking at this person, Doris Smith, and, here her basic information about who she is. But this is mapping out her healthcare journey through the system that she participates in. So, she enrolled in this program, this health insurance program. She's had a periodic wellness checks. And there's a warning here because it looks like she missed a month. She went like 2.5 months, almost 3 months, without having a wellness check. So that's something to be concerned about for somebody at her age and her general condition. These are when there were financial claims to pay for those services, and there's pharmacy. So she had drugs from the chemist that she was supposed to get, and she actually, for her service, it's recommended that she has in-person visits with a healthcare advisor. And again, there was a gap here, so there are some warning signs. So we're looking at her journey. We're looking at, is this an example of a good or bad case? Well, we'd have to say at least here there's some bad events, and we want to see is, okay, what could we have done to prevent this? Could we intervene somehow to make sure that these gaps don't happen? Was there some outside condition, like she wasn't, she traveled out of area, for example? And once we figure out best practices, or we figure out a condition that deserves someone to intervene, to pay attention and maybe, try to contact her, we want to find similar people. So this dashboard has a find similar members button built into it. And we actually have a mock-up of a similar thing where we've applied it to a different use case. And this is being used by a sales organization to track, in this case, the journey of their sales leads and prospects, to see if they're moving through the system well, to see which ones can we convert from just being prospects into paying customers. And they have a number of different types of activities they can focus on. They can set a date range, and we also actually, in an earlier Graph Gurus, in Graph Gurus 20, we went over this little sample application, and this is in our Customer 360 starter kit, which you can get on Tiger Graph Cloud. You can actually use one of the free instances on Tiger Graph Cloud to try this out yourself. So you can go watch the Graph Gurus 20 episode. You can go to Tiger Graph Cloud and try the Customer 360 dashboard. So I'm just going to very quickly run a couple queries here. This first one for customer journey subgraph. And what this is going to tell me, it's going to show the activities that relate to this, oops, that's wrong, to this person, Sam Eisenberg. Delete that, try this again. And hopefully I copied this right. Okay, and so this nicely maps out. There's Sam, and here are various, the type is campaign member. So that is a member of the campaign, an entity, and these are referring to specific things like an AML webinar, a fraud detection / AML webinar, etc. And these also have a time, so they could be, this is not necessarily organized by time, but they could be. And so let's say this one turned out to be a case that did become a customer. Sam did become a customer. So then you want to find out, well, where can I find similar people at this stage? And so I can make sure I do the right things so this person also becomes a customer. So then we actually wrote a query based on the Jaccard similarity, and I'll tell you more about Jaccard similarity later. And so again, we put in Sam's information, his name, and we describe a couple things here that we're interested in, a couple campaign type things. Webinar, and also this one says demo sign up trial, and I want to find the top 5, and it finds these 5 other persons. Now, looking at this display, you can't see anything. In this case, you really want to look at the textual output or the JSON output. And so here we see the names. So this is Priyanka Patel, and she has a similarity score of 30769. The next most similar person is Scott Tate. You see you have a couple other persons with the same similarity score, Vincent Chen and Helen Fisher, and finally Damien Valderrama. So that gives you your next best opportunities to pursue. So that's one application why you might want to use similarity, why there might be a business need. Other cases, finding similar investment opportunities. So you can, again, try to be successful again by repeating the same things, or at least improve your odds. Find out things to avoid. Fraud, of course. We find a certain individual turns out to be some sort of fraudster, and you want to catch similar persons. So again, you want to analyze your data to find similar situations. Now, how do you model that? Now, if you've got traditional tabular data, that entity of interest, whether it is the healthcare patient or the fraudster or an investment opportunity, so that might exist in some table. But the characteristics, the factors that make that entity distinctive probably require that you join with other tables. So, it can be done, but it's a lot nicer, a lot easier to understand and to work with if it's a graph structure, because then you have this simple hub and spoke pattern where the entity of interest is the hub and these other factors just connect to it either directly, one step, or maybe some of them are two-step relationships. But it's very easy to see visually, and it's much easier to write the query to find these things than to try to write it in this way. So, and we'll talk about one additional benefit when you're not even sure what the factors are. So it's great if you know what are the telltale signs to identify that person, but if you don't even know, then what do you do? So I mentioned earlier that conceptually, saying two things are equal or the same is easy. Just everything you know about them should be identical. However, in the real world, that's really not what you're looking for. I'm not looking for another fraudster who has the same name, obviously. I'm looking for a different person, but where the important characteristics, the behavior they engaged in, for example, is the same. So, and it's also, it doesn't have to be an exact match. So it's that similarity. Well, how similar? How do you measure similarity? Like, what does it mean to say something is 90% similar? How can you quantify that? Well, we're going to quantify it according to some particular criteria, and I'm going to explain to you how we quantified it, but I'm not going to tell you that's the right way to do it. Only you can answer whether that's the right way to do it, but we'll give you some guidelines. So similarity is in the eye of the beholder. What factors do you care about, and which ones are more important than others? What is their relative importance? So I'm talking about sort of the factors, so to speak, but probably the one that you're most interested in is the outcome, so to speak. Like in that case, what happened was we took a patient who had a particular, a potential critical health condition. but by applying the right care in the right sequence, we were able to bring that person back to health. Or I found, this turned out to be a successful investment, or that is a fraudster. And that's the outcome. The outcome was fraud. So then you look at, okay, what factors drive that outcome? That sounds like a machine learning problem. And so you can use this in combination with machine learning. But the graph-based approach in general is great for this because it easily shows you all the known associations. So you don't know which ones matter yet, but you've got all of them at your fingertips. Again, remember that hub and spoke model. There's my entity. There are all the activities that surround that person, and you can go 2 levels deep. You can go 3 levels deep, but there's everything you know. And then, maybe you have enough knowledge of your field that you'll be able to look at the data manually and say, okay, I know what caused that. Or maybe you need to, combine it with machine learning. But the graph model is sort of the first step to help you with this. And this is just a little illustration of where I said, it's up to you to decide what similarity matters, or at least it's application dependent. So let's look at this question. Which is more similar to the hippopotamus? Is it the whale or the pig? And, I would guess most people would say the pig, both land-based, both not covered with, both mammals, but not covered with fur. None of these are covered with fur, but at least these both have 4 legs. So the question is, if you look at sort of ordinary human observations, what a biologist would call phenotype, the ordinarily observable characteristics, the phenotype, you'd probably say it's the pig. But if you look at the genes, the genotype, that's the whale. Genetically, the whale and the hippo are much more similar. They're cousins than the pig and hippo, who are second cousins. So depends on what factors you look at. So let's get into some examples. So I'm going to start with Jaccard similarity and cosine similarity, probably the 2 best known similarity measures. And then we'll do some graph-based variants of those. So Jaccard similarity counts how many features 2 entities have in common. So the mathematical formulation typically looks like this, where f of a means the feature set of a. And so translated that into more normal English, you're counting the number of features that A and B have in common. How many features do they have in common? Divided by the total number of distinct features in either A or B. Visually, you can think of it this way. If the feature set of A is represented by that blue oval and the feature set of B is that reddish oval, the overlap where they both have the feature is that area. That's the numerator. The denominator is what could be a feature in either A or B. That's the union, and that's the intersection. And so you can see the range of values is between 0 and 1. And this is really used when you don't really, remember, you're counting the features. You're not scaling them numerically. You're just saying yes or no. Do I have this or not? And so here's an example. And this is a classic market basket example where I have 3 baskets with these different groceries, and I just count the overlaps. So the Jaccard between 1 and 2 is, okay, what do they have in common? They both have bread and they both have bananas. And then how many total items are there? It turns out there's 7 total items. So the score is 2 divided by 7. If I compare basket 1 and 3, I see the only thing they have in common is mushrooms. They have a much lower overlap. So only 1 item out of a total of 8 items. So the score is 1/8. So that's Jaccard. It's pretty simple. Anybody could do that. Now, cosine similarity gets a little more complicated. And this is when you do have numerical values and you're looking at degree of closeness in that way. And the formulation, that nice shorthand vector notation looks simple. When you spell it out, it looks a little scarier. So remember, you're thinking of now for each item, instead of just saying I have a set of non-numeric properties, I now have a list. So it's a sorted list in order, a list of scores or numerical values. And now you're comparing how similar is one vector, the vector of A, to the vector of B. And you're doing it this way by, in the numerator, you're comparing them element by element, the first element of A times the first element of B, then plus the second element of A times the second element of B, and so on until you get to the end of the list. And then you divide them by, if you think of each one as a vector, you sort of use Euclidean distance, squared, sum of squares, roots of the sum of the squares. And why do we call it cosine? If you think about this is a cosine wave, when you're at 0, when you're at angle 0, the cosine value is 1. When you're at angle 90 degrees, then the cosine is 0. And when you're at 180 degrees, then the cosine value is -1. So that's actually a negative score. And when you think of those list of numerical values, those vectors, this way, let's say we have short vectors of they're only 2 elements. So A is the vector 6, 2, and B is the vector 4, 4. And you graph them, on an XY grid. And what we're doing is we're actually measuring the angle between these two. So you can see if A and B were the same, then the angle would be 0. Well, the cosine of that angle is then 1. So their similarity would be 1. Now, if A were like along the x-axis and B were along the y-axis, then there would be 90 degrees between them, nothing in common, and then you get your score of 0. And this is, again, computationally, the example 6 times 4 plus 2 times 4. That's the numerator. Denominator, we do the root of the squares, et cetera, blah, blah, blah. And you can check yourself later that that's the right value. So you see, overall, Jaccard is when you're counting features, and cosine is when you're comparing feature sets numerically. Now, how do we do a graph-based approach to this? In the graph-based approach, we're going to think of those features as the neighbors. The neighbor set is the feature set. So now for A, my feature set is who are my neighbors? My neighbors are W and Y and Z. So A's neighbors, W, Y, and Z. B's neighbors are W, X, and Z. And now I'm going to perform the Jaccard similarity on these two sets. So what do they have in common? They have W and Z. And what is the total combined set, the union of those two sets? And that has 2 items, that has 4 items. So the Jaccard similarity score is 2 divided by 4, or 0.5. Now I colored these two differently because realize now we're thinking of A and B as one type of thing. Those are the entities of interest. And it's possible that W, X, Y, and Z in your data set, they are the same type of entities. These could all be persons. These could be, excuse me, 6 different persons. And you're just counting who do you know. But they also could be different entities. They could be a different animal, so to speak, where they could be books you've read. So the orange could be persons and the blue could be books, and that would work just as well. Now let's using the same graph, let's apply cosine similarity. So the difference here, of course, is now we're using the edge weights. So now we're going to pay attention to these weighted edges. So if I define the vector as the weights to W, X, Y, and Z in that order, so then A's weights are 2, and it has no connection to X, so that's a 0. Then its connection to Y is 4, and its connection to Z is 1. And again, what do these mean? These could be strength of relationship. If this is persons, it could be, you know, how long you've known them, how well you like them. If they are books, again, it could be your score. How well did you like that book, or how well did you like that restaurant? In fact, that's starting to sound like recommendation. I think one of our very first graph gurus might have even been I can't remember, it might have been number 1, was on a recommendation system using cosine similarity. So A scores 2041, B's vector is 3102. Apply the formula, multiply, that's 6002. That's how I got the 8. And then square, 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 sum, square root. That's 21, that's 14, get that score. Now, let's get a little more advanced. So again, just to quickly review, what did we just do? We took the well-known Jaccard similarity and cosine similarity, and we applied them to graph by thinking about neighborhood relationships. There are other ways. So the classic way is that just, it's not even a graph. It's just A, there's some properties of A, you list them out, and you can compute Jaccard and cosine with a list of properties. They don't have to be graph properties. But here we took advantage of the fact that we have these built-in graph features. So let's get a little fancier. So those were both local measures. They're looking just at immediate neighborhood. And some people said, similarity is deeper than that. It's not just looking at your immediate neighbors. It's looking at really, where do you sit within this ecosystem? And so one measure that researchers came up with is called SimRank. And it starts with the idea that number 2 really expresses the basic idea. 2 vertices are similar if they have similar neighbors. So it's a recursive definition. You can't say independently something is similar. You have to first look to its neighbors and say, are the neighbors similar? And if you know the neighbors are similar, then these 2 entities are similar. But how do you know if the neighbors are similar? So that's why it's a recursive definition, and that actually follows very much with like the PageRank definition. So, and you can compute it like PageRank. So you start with the idea that saying an entity is perfectly similar to itself. So the SimRank score of any vertex to itself is 1. Any other pair will have a lower score. And this is the definition. So the SimRank score for any 2 vertices, U and V, it's some constant. This constant is between 0 and 1, typically 0.6 to 0.8. Times, it's usually not said this way, but I'm saying it this way because I think it's a lot easier to think about. It's the average of all the possible pairs of neighbors of U and neighbors of V. So A is now I wrote in parentheses. You can define it either as the neighbors in general, or if you have a directed graph. The original authors of SimRank used it on a directed graph, and they looked only on in edges. But fundamentally, there's no reason why this formula wouldn't also work on out edges or on an undirected graph. It changes the interpretation slightly, but the concept still works. So you can feel free to use this either on directed or undirected graphs. So the set A is the neighbors of U, and B is the neighbors of V. And you compare every possible pairing of a neighbor of A with a neighbor of B, and then you average those scores. And so the first time around you go through, if A is not equal to B, that's going to be 0, right? It's only if A equals B, then it'll be 1, because that was our initialization condition. So it turns out sometimes it basically ends up saying, do you have any neighbors in common? If you have any neighbors in common, they're going to have a 1. If they're not the same person, it's going to be a 0. So you'll end up, after the first round of computation, some of these will be fractional scores between 0 and 1. And now I have a fractional score for UV, and UV is the neighbors of somebody else. UV is the neighbors of FR or something. And so the scores keep changing and eventually converge, just like PageRank. So let's look at an example. So AB, same graph, sim rank of AB is it's C times the average of all the possible pairings. A has 3 neighbors, B has 3 neighbors, so there are 9 possible pairings. Only in 2 of those cases will they coincide on the same person. W is a neighbor of both A and B, and Z is a neighbor of both A and B. So in 2 of these 9 cases, you get a score of 1. The other 7 cases, you get a score of 0. So after the first round, the score will be 2 times the constant C divided by 9. And again, because there's 9 possible neighbors and 2 of them are shared. And then you repeat, you do another iteration that'll refine the scores. Eventually they'll converge. So let's make some general comments about these 3 methods, because SimRank is actually kind of similar to both cosine and Jaccard in some ways. Now, cosine and Jaccard, as I mentioned, they're both local computations because they only look 1 neighborhood deep. SimRank looks deeper. Each iteration, it's like it's taking a second or third hop. So each iteration is going 1 hop, and each subsequent iteration is going another hop. It's refining both the first hop and looking at another hop. And if you go do enough iterations, you've looked at the whole graph. You actually do look at the whole graph even in the first round, but you keep refining it and refining it. So SimRank is computationally more expensive than cosine and Jaccard. Cosine and Jaccard are pretty cheap. SimRank takes a big step up in the amount of computational effort. There are personalized versions, so where you focus on, well, I don't need the whole graph. I just want to find out who's similar to me. And that's a little bit less expensive. And also want to mention, they kind of work with bipartite graphs well. They can work with monotype graphs where, like a social graph, every vertex is a person, or they work well with bipartite graphs where you have people and products. Now, there's one drawback of SimRank, from my personal opinion, is that it penalizes you for having more neighbors in common. And let's think about that very quickly. I said here A and B each have 3 neighbors, so there are 9 possible combinations. Let's say they actually had exactly the same neighborhoods. A had XYZ and B had XYZ. Then I have 3 matches out of 9 combinations. So my score is C times 1/3. Even though it's a perfect match, exactly the same neighborhoods, SimRank tells you the score is 1/3. And you can see the same thing. If you have 4 neighbors, SimRank tells you the score is 1/4. The more things you have in common, the lower your SimRank score goes. That's kind of counterintuitive. That's sort of my personal thing I don't like about SimRank. And so the last thing I'm going to do before we go to demo is talk about a little bit higher form of structural similarity. So look at these 3 family structures here. The 2 parents and either 2 children or 3 children in each family. And just looking at them, you kind of say the Smith family looks structurally equivalent to the Jones family. They have exactly the same structure. And in fact, there's even a connection between S1 and J1. So there's even a way that you can link them. Now let's look at, how about the children? Is S3 similar to S4? I happen to put this on the left and that on the right, but you could flip them and the graph would still be, it would be the same graph. It's sort of arbitrary that I put one on the left and one on the right. That kind of tells you that these are identical in some sense. So these are structurally equivalent. Since the family overall, the Jones family, is like the Smith family, should I then say that J3 is similar to S3? Pretty strong. Maybe not as strong as S4, but still strong. And again, the Lee family, you see the same concept, but it's been stretched a bit. Now there are 3 children instead of just 2. So you intuitively, you want to say they're similar, but not as similar as these 2. So there's another algorithm called RollSim, which takes all those things into account. And you know, if things are structurally similar, like that Smith to Jones family, it's going to give them a score of 1. It's going to say those are perfectly similar. So it's not going to have that same score penalty that SimRank is. You know, full disclosure, this is research work that I did. This was actually part of my PhD dissertation. So what it's doing, instead of looking at all possible pairing of neighbors, it looks for the optimal pairing. So again, talking about if A and B each have XYZ as their neighbors, RollSim is going to identify that and say, this is a perfect match. It gets a score of 1. How does it do that? There's a little sub algorithm called maximal matching. It's more complicated than a simple averaging, so it takes more computational work. So it's even slower than SimRank. So it's mathematically nicer, has nicer properties about the meaning, but it does take more effort to compute. So since I think we need to get to the demo. So I'm gonna go to my demo now. So I'm using the same data set that I used in some of the previous ones, the airports. And the Jaccard, if you go to the tigergraph graph algorithm library on GitHub, you can see, what do we have here? Oh, I was already, sorry. Algorithms and examples, and we're doing similarity. So see, we have several variations of cosine and Jaccard. So I'm starting with just the basic one called Jaccard neighbor, and SS stands for single source, which means we start from one vertex and we give you a Jaccard similarity score comparing this vertex to every other vertex in the graph. And then you can look at which are the top, to which other vertices is it most similar. And you can see it's a relatively short algorithm, not a whole lot of lines. I did tweak it for our airport route use case. The tweaks I made is I wanted to make the types of data you use a parameter. So you specify the vertex type and specify the edge type, though I do have default values. And I put in a default value for the top number of items. And I also improved the output, so it's a little bit easier to identify who is that entity that I'm similar to, rather not just using a coded ID, but showing a more human readable ID. So let's see, I'm going to start with, now some of you know I live in Ohio. I live in Northeast Ohio, so I often fly out of Cleveland Airport. However, that's not the only airport I fly out of. It turns out I'm just a little bit further away. It's not much longer for me to drive to Pittsburgh. And within the sort of the network of what function do they serve, it's actually pretty similar to Pittsburgh. As you can you can fly to the same cities. I can fly from Cleveland to San Francisco nonstop, or I can fly from Pittsburgh to San Francisco nonstop. But here's some other airports, which interestingly are all in the US, because remember, it's looking at combinations. Jaccard is looking at who do you have in common. So the one that it gave the highest score was Cincinnati, which is also in Ohio, Raleigh, Baltimore. So, and we could look a little bit more closely at the network to see why it thought Cleveland. Let's see if I can save these results. I have another one called Who Do You Have in Common, which is called Common Neighbors. Oh, great. Oh, I have to install it. I don't want to do it right now. Maybe do it a little bit later if I have time. So I want to just compare this to now the cosine, though. So let's use the same. Let's use Cleveland also. And see what result I got here. Again, Cincinnati, but Pittsburgh moved up. And now I'm using numerical scores. What am I using? I'm using the distances for each flight route, because remember that was one of the pieces of data that we have. So if I go back, actually, if I go here and enter in, actually, what's Cleveland's ID? Oh, shoot. Jaccard. It was 3486, right? Cleveland is 3486. The reason why I want this here is Cleveland 3486 airport, and then a whole bunch of flight routes, and I show miles. Oh, you know what? Rather than showing that visually, I created a query to show this way. This is easier to read. Cleveland. So you can see these. So I said in cosine similarity, you need numbers. So what are we using? We're using these numbers. We're using how far is it to each of these cities. So if two cities have similar Jaccard similarity scores, what it probably means is that not only do they tend to fly, high cosine similarity, not only do they tend to fly to the same cities, but they're about the same distance to those cities. And since Cleveland and Pittsburgh, sort of in the scope of ranking of importance of cities, they're kind of similar. They're not major airports like Los Angeles or Las Vegas even. They're more minor, but they sort of have this approximately the same importance regionally, and they're close. That means the distances are going to be similar. So that's like a high justification for saying, why is it that they have similar cosine similarity scores? Now, I ran another example here. Let's see, make sure I'm running the right one. Nope, and do one more. Jaccard cosine neighbor airport. London, I wanted to make sure I did some not in the US. So London City Airport, you know, it's not Heathrow, it's not Gatwick, it's one of the lesser airports. In fact, it flies, this database shows it flies to 36 cities, whereas obviously Heathrow flies to hundreds of cities, if not 1,000. So here we're trying to find who is it most similar to cosine wise. Southend, Heathrow, and Gatwick. So interestingly, yeah. So since this is also a London airport, gave a high score for London, Heathrow, and Gatwick, and then Cardiff. Interestingly, even though it has a much lesser role, it's not as important in airport. It's still, for the places it does fly, it's sort of similarly located. So let me try one more, see what LCY does here. And now this time I think I get very different answers. So now, now probably what matters more is the distances don't matter. It's just, do you have a lot of overlap to places you fly to? And now you're seeing these smaller airports, which, because this is not a big major airport either. So these tend to, it's flying from a secondary airport to another secondary airport. And again, because distances don't matter, these are probably all shorter flights. And that's another thing to think about. We counted longer distances as more important because we chose to use distance as our numerical measure. That may not really be what matters, but that's the number I had available. That's the number I used. So that's, again, a cautionary tale about really thinking about, well, what should I be using for my scores. And another thing I want to mention about cosine similarity is, so you have a vector, and you have, like, say 3 fields in your vector. Say it's characteristics of a person: height, weight, and age. You want to normalize those. And because think about it, even if you do a height, are you measuring in inches or centimeters? That's going to affect your number. Weight, are you measuring kilograms or pounds? And just changing the units you use changes the number, and it can make a number bigger or smaller, but it shouldn't make it more or less important. So you do probably want to normalize those, which means, like, think about what's the average and then the standard deviation from average. And lastly, I want to show SimRank. And so I need one airport. Let's try, and this time I have to use the full ID. That's just the way I wrote this one. And I'm limiting it. I'm doing a little bit of filtering. And the reason why I said this is a more expensive algorithm, I tried running it on the whole graph and it was taking too long. So I did a couple things. I'm looking only in the United States. In fact, I'm also only looking at airports that directly connect to Chicago O'Hare. And so what I'm trying to do is, among all these airports which connect directly to O'Hare, which one is structurally the most similar to Canton Akron Airport? And maybe I could use a little bit of time sort of visually show you. I've been talking about where these cities are located. I haven't visually shown you. I can try to show you, or I can just answer questions. So what it found out is that the highest SimRank score is actually with Atlanta, which is interesting because Atlanta is a major, it's one of the busiest airports in the world. So where Canton Akron is nowhere close. Detroit is also, at least it's a US hub. Houston is a hub. They're both international airports. This is Washington Reagan. So it's important within the US, but it's actually not nearly as important as Dulles, which is the main international airport. So interestingly, it thought Atlanta. Now, one thing is, because that was only 3 iterations, that probably wasn't enough. I did 3 because there's sort of a default timeout for how long a query can run before it'll automatically stop. You can increase that, but I didn't want to go into those advanced settings. So these even might not be the best answers because this only did 3 iterations. It probably did not really converge to the final answer. So again, that was a bit of a surprising answer. So, but in any case, these are all algorithms in our graph algorithm library. I did a little bit of personalization just to have them run here. And I will be just like I've done for the previous webinars for webinar 26 and 27, shortest path and centrality. I've published all the files for those. And in the next day or two, I will be publishing the files for Graph Gurus 29 on community detection and this one on similarity. So again, one of the messages I want you to walk away from is remembering that similarity is in the eye of the beholder. It depends on what factors matter to you. The graph model is a very effective model for thinking about similarity because of the hub and spoke view. Makes the features very accessible. And I want you to understand the difference between Jaccard and cosine similarity. One is counting matches and the other is measuring numerical alignment. And then 2 ways of doing a deeper assessment are SimRank and RollSim, which define similarity recursively. They each take multiple hops and they also look globally, so they do take more time to compute. And thank you for your attention. And if you have any questions, I would love to answer them.
Thanks, Victor. That was very thorough and fluid. Let's see, we have a few questions from the audience. First one here is, how would you use similarity algorithms with machine learning?
Ah, great question. So one thing I said earlier was that the graph model at least shows you all the relationships that are available to you, but it doesn't tell you which ones are important for your similarity measure. And that's a classic setup for machine learning. So one thing you can do is there's actually something called weighted cosine similarity. So I mentioned earlier also about figuring out normalizing, making each field, each attribute or property equally important. Well, maybe that's not what you want. What you want to do is actually find out which one is more important than the others for the purpose of getting your desired outcome. So you can do supervised training with this. So basically, create a vector which shows just what are the relationships. So each neighbor and each weighted edge can be one member of that vector. You can add other features as we've talked about in other webinars. You then put that into your supervised training program, identifying which of these gave you the desired result. And then the output of that would be weights. And then that tell you, apply these weights to get the best prediction for, so take your feature vectors and multiply the different fields in the vector by these weights, and that becomes your predictor for whether this will generate the desired outcome or not. And then every time you have new data, you can apply those weights to that new entity's feature vector, and you have your prediction. So that's one classic way.
Interesting. Here's another question that we have. How do similarity algorithms compare to graph pattern matching?
That's another great question. I wonder if I should show some sort of picture here. So when we talked about some person's journey, so we can use this. So so the question here, that might be just two different questions you're asking, but for the same basic issue. So is the question, hey, S2 is a person of interest, who else in the graph is similarly structured as S2? And the answers would be J2 and L2. But maybe your question is, here's a family of interest, find other similar families. So these similarity algorithms we've been talking about have been focused on individuals. Find a similar individual. Pattern matching is where you would write a query which somehow describes perhaps this whole family. You know, S of a certain type, S1 of a certain type is connected to an entity of a certain type. So you'd be describing 4 entities and what, 5 relationships. So and then the answer would be Jones family, Lee family, with different scores. And so it's actually closely related. So it would, obviously, it's probably trickier, or at least computationally harder, to find the Jones family as being a match to the Smith family. But you can do that. You can do that with Tygrograph's pattern matching, path matching syntax. Just expect that query is going to take longer to compute. I hope that answered the question. And so basically, yeah, in the from clause, you would need to describe this whole little pattern of having 4 entities and their types and their relationships.
Mm-hmm. Interesting. Okay, well, I think in the interest of time, we should wrap up. There were a couple more questions from the audience, but we'll reach out to people individually. So why don't we move on, Victor, and wrap things up?
Oops.
Okay, great. So if there are more questions, we invite you to join our developer forum. We're putting a lot more emphasis behind that forum, and we'd love to hear from you in that manner. And additionally, we hold office hours, developer office hours, each Thursday at 11 a.m. Pacific time. And that's a great opportunity for you to ask a question in an online manner to one of our subject matter experts and have immediate answers, and indeed go further and even engage in a dialogue. Again, every Thursday at 11 a.m. Pacific. There are some additional resources. TigerGraph Cloud is a fantastic way for you to get started with TigerGraph. It's convenient, it's free, it's engaging. It takes about 5 to 6 minutes to open an account on TigerGraph Cloud. And if you haven't already done that, I highly recommend you do so. There's no cost whatsoever, so really no reason not to do that immediately after this webinar concludes. Additionally, you can use one of the solutions, pre-populated solutions, in perpetuity for free. And when I say pre-populated solution, what I'm referencing is a number of, is our starter kits. Currently, we have 18 starter kits across different use cases. These starter kits are pre-populated with graph schema, some sample data. The schema can be changed by you if you need to. The data can be replaced with your own data, and so on and so forth. And so these pre-populated solutions are a fantastic way for you to begin to, dip your toe in the ocean and begin to develop familiarity with graph. And if you want to have more than one solution, you can enter a credit card and then use multiple solutions. We'll even give you a $25 credit. So really, if you think about it logically, there's no reason not for you to do that immediately after the webinar ends. It's a fantastic way to begin to develop familiarity with graph. Additionally, we have test drive demos. These are online demos, again, looking at specific use cases. And you can both see a video demonstration from Victor and others, and then you can begin to try to develop the same capability, replicate the capability. It's another way to help you to get started. You can download the developer edition, and there are some graph scripts that help you to get going faster with TigerGraph. And last but not least, we have some in-person events. We call these Graph Gurus Comes to You. We have an event coming up shortly in London. We have one in San Francisco, Seattle, and more. And you can even request that we come to a city near you by clicking on that URL. When we send out our email after this webinar, we'll include the slides, and you can click on that URL in the deck, go to our website, and you can request an event in your location. And our next webinar will be next week. It's going to be an especially interesting one because we have a customer joining us, and we have John Herkey, who's our evangelist, developer, technical evangelist, hosting, and that the topic is using Giraffle to manage deployments at an enterprise scale. Next Wednesday, March 11th at 11 a.m. We would love to see you there. So that brings us to the end of the webinar. I want to thank everybody who's stuck around to this point. I know we're a wee bit over time. We know that you have many things to get through today. We're flattered that you've chosen to spend the past hour with us. We hope our enthusiasm for graph has rubbed off, and we invite you to get started with TigerGraph in the ways that we've just described. We hope to see you at a future webinar or even at one of our in-person events. But for now, that's it. Thank you for joining us today.
Thank you very much.